AI doesn't actually understand words the way you do. It works with numbers. So here's the interesting question. How do you take something like a sentence, an image, a piece of code, or even an entire document, and turn it into numbers without completely losing the information inside it? That's where embeddings come in. An embedding is basically a numerical representation of information. Take these two sentences. I love dogs. I really like puppies. The words are different, but the meaning is pretty similar. An embedding model takes those sentences and converts each one into a long list of numbers called a vector, something like 0.21 minus 0.47, 0.83, 0.12, minus 0.36. Of course, a real embedding can contain hundreds or even thousands of numbers. And here's the strange part. Those numbers don't mean much to us individually. You can't look at one number and say, this is the dog number, or this number represents happiness. That's not how it works. The useful information is distributed across the whole vector. And that gives us a very interesting way to think about embeddings. Imagine a gigantic mathematical map. Every sentence gets placed somewhere on that map. Every document gets a location. Every image can get a location. Every piece of code can get a location. And the location is determined by the information and meaning captured by the model. Now suppose we have these three sentences. I love dogs. My puppy is adorable. I need to configure a Linux server. The first two would probably end up relatively close together. The Linux server sentence would be somewhere else, not because the system has a human-readable label saying, these are about animals. It's because the patterns in the information produce vectors that are mathematically closer, and that is the key idea. Similar information tends to produce similar vectors. Different information tends to produce different vectors, so embeddings turn something that feels very abstract to humans, like meaning, into something a computer can compare mathematically, and that's where things get really useful. Let's say you build a search system. You have thousands of documents. A user searches, how do I repair my automobile? But your best document is titled, how to fix a car engine. A traditional keyword search may care a lot about the exact words, repair versus fix, automobile versus car. But an embedding-based search can look at the meaning. It converts the user's query into a vector. It has already converted the documents into vectors. Now it simply looks for the vectors that are closest to the query. And suddenly, the document about fixing a car engine can become a very strong result, even though the wording isn't the same. That's called semantic search. You're not just searching for matching words, you're searching for related meaning. And this idea is everywhere in modern AI. Search engines use it. Recommendation systems use it. Document retrieval uses it. RAG systems use it. Code search can use it. Clustering can use it. Even systems that detect similar or duplicate content can use embeddings. Now let's look at RAG, because this is one of the most practical places where embeddings appear. Imagine you have a large collection of company documents, maybe thousands of PDFs, manuals, policies, and internal documents. You don't want to send all of that information to a language model every time someone asks a question, so you first break those documents into smaller chunks. Then you create an embedding for each chunk. Those embeddings are stored in a vector database. Now a user asks, what is the company's policy for laptop replacement? The question itself is turned into an embedding. The system compares that query vector against the stored document vectors. The closest ones are retrieved, and those relevant chunks are then given to the language model. The language model generates the answer using that retrieved information, so the embedding isn't necessarily answering the question, it's helping the system find the right information. That's an important distinction. The embedding is more like the index. The language model is the one generating the response, and this explains why you hear the term vector database so often. A vector database is essentially a system designed to store these numerical representations and efficiently find nearby ones. You can think of it as a search engine for vectors. Instead of asking, which document contains these exact words, you're asking, which stored vectors are most similar to this vector? There are different ways of calculating that similarity. One common method is cosine similarity. You don't really need the formula to understand the idea. It basically measures how similarly two vectors are oriented. More similar direction usually means more similar representation, and that gives us a similarity score that the system can use for ranking results. But here's an important thing people often get wrong. An embedding is not a perfect representation of meaning. It's a representation created by a model, and models have limitations. A sentence that seems obviously related to us may not always produce the result we expect. The quality of the embedding depends on the model, the data, the domain, and even how you prepare the text. For example, document chunking matters. Suppose you take a technical document and split it in the middle of an important explanation. One chunk contains the question, Another chunk contains the answer. Now you've separated information that really belongs together. The embedding model can still create perfectly valid vectors, but your retrieval system may perform worse because you've broken the context apart. So building a good semantic search or RAG system isn't simply generate embeddings and you're done. There's much more involved. What should be embedded? How should the documents be split? How large should each chunk be? What metadata should be stored? Which embedding model should be used? How many results should be retrieved? Should semantic search be combined with traditional keyword search? These choices can have a huge impact on the final system. There's another interesting detail. Not every embedding model produces the same kind of vector space. Suppose you embed all your documents using one model. Those documents now live in that model's representation space. If you suddenly switch to a completely different embedding model for your queries, the vectors are not automatically compatible. The numbers may look similar. The dimensions may even look similar, but they don't necessarily represent the same space. So in many systems, changing the embedding model means generating the embeddings again. That's an important practical detail that can easily be overlooked. Now, embeddings aren't limited to text. The same general idea can be applied to images. Imagine thousands of photographs. An embedding model can convert them into vectors. Now, similar images can be found near each other in the vector space. The same concept can apply to audio, or code, or other forms of data. And this opens up some very interesting possibilities. Imagine searching for a product using a picture instead of words, or finding similar pieces of source code, or finding documents that are semantically related even when they use completely different wording. The underlying trick is still the same. Represent the information as vectors, then compare those vectors. And there's an even deeper perspective here. Embeddings aren't really about numbers, they're about relationships. The numbers are just the representation. What we actually care about is the structure created by those numbers. Which things are close? Which things are far apart? Which groups naturally form? Which pieces of information are unusually different? Once the information is represented as vectors, you can apply mathematical operations to it. You can search it, you can rank it, you can cluster it, you can find similar examples, you can detect outliers, and that's incredibly powerful because normal human information is messy. Text doesn't naturally look like a database. Ideas don't naturally come with coordinates. But embeddings give them coordinates. That's why the phrase embedding can sound much more complicated than the underlying idea really is. You're essentially taking information and placing it somewhere in a high-dimensional mathematical space. Now imagine doing this not for 3 sentences, but for millions of pieces of information. You suddenly have a huge map of relationships. Some points are close, some are far apart, some form clusters, some sit between clusters, and those patterns can become useful for AI systems. That's why embeddings became such an important building block of modern AI. Large language models get a lot of attention because they generate text, but behind many useful AI applications are systems that first need to understand which pieces of information are related. Embeddings provide a way to do that mathematically. A user asks a question. The question becomes a vector. Your knowledge base contains millions of vectors. The system finds the closest ones. Relevant information comes back, and only then does another model generate the final answer. So when you hear terms like semantic search, vector database, RAG, similarity search, or document retrieval, there's a good chance embeddings are somewhere underneath. And the easiest way to remember all of this is with one simple picture. Imagine a giant map. Every piece of information becomes a point. Similar things tend to live near each other. Different things tend to live farther apart. The computer doesn't need to read the words the way a human does. It can compare the coordinates. That's the real trick behind embeddings. They turn meaning into a mathematical relationship. And once meaning becomes something you can measure, AI can search it, compare it, rank it, and use it.